should we check in about Halloween? Happy Halloween.
Happy Halloween.
And also remind people to vote. If you're listening to this on Monday, tomorrow is an election day. Go and vote.
All right, you want to do the proper intro?
Okay, yes. Hi, my name is Linnea.
I'm Bezia.
And I'm Linnea, and this is episode number 5 of the Lemma Journal Club, the show where we read every paper to let you know if you need to read it. You probably do.
We have a terrific paper for you today. We are talking about the research paper Volumetric Imaging of the 3D Orientation of Cellular Structures with a Polarized Fluorescence Light Sheet Microscope. It's published by, again, a ton of people, so I'll just go with Talon Chandler is the first author, and Harry Schroff is the last author. And then I'll also shout out that Rudolf Oldenburg is on this paper because I think yesterday an MBL position came up that looks a heck of a lot.
You're stealing my thunder here.
Oh, okay. Why? So I will say I was supposed to pick the paper this week. I decided that my paper nobody was going to like because it was too physics and not enough biology, which in retrospect is a very silly thing. And so you ended up last minute picking this paper. Lydia, why did you pick this paper?
So I picked this paper because just a few days ago we saw that there's a posting for a faculty position at the MBL looking for a person who's developing new kinds of optics. And we started talking about what that would mean if we wanted to apply for it and what kind of things we would be excited to develop for our research and for the community. And so I know that Rudolf, who is currently at the MBL, does a lot of optical setup creation. And so I Google Scholared his recent papers, and this is the one that seemed the most interesting and relevant to us, and that's why I picked it.
So I think I had looked at this paper previously. It's been out close to a year now. I didn't understand this paper at all when it first came out. I read it much more carefully this time for this journal club, and it's quite a simply written paper for how complicated of a thing it is.
Yeah.
All right. So now for our quick segment we call Speed Read. I'm going to summarize the paper with a reading of the in brief abstract as quickly as I can. This is in PNAS. I don't think I said that. In PNAS, the paragraph is called Significance. So here's the significance paragraph. Cells rearrange their constituent molecules to create dynamic three-dimensional structures critical to their function. Muscle and brain tissue, for example, rely on anisotropic chemical, mechanical, and electrical properties that often coincide with optical anisotropies and isotropies revealed by polarization-based microscopy, including polarized fluorescence. While most such microscopes are limited to measuring a subset of orientation parameters, we built a microscope that can assess the complete 3D orientation and position distribution of assembles of fluorescent molecules. We demonstrate and validate this technique by imaging labeled membrane cellulose and actin, proceeding to study cell growth on nanowire grids. We find that actin orientations at the smallest measurable scale are correlated with the large-scale orientation of the entire cell, revealing unexpected coordination across scales. I feel like I should be timed for these.
Okay.
And that there should be some sort of over-under reward if I manage to read it fast enough.
Okay. This segment, I think, needs work. I just think it's too fast. And we can call it speed read and read at a accelerated but not
you want
a
the
ridiculous
speed read to be slower
clip. Yes.
I was trying to go for that. I would practice it a lot, and eventually the speed read would have a announcer to a horse race kind of voice into it. Maybe I get an old-timey voice filter so that it sounded like that.
Maybe if that was the reality, I would be more on board.
Okay, one of the things I like about this paper right off the bat, again, it's a PNAS paper that has hit the 12-page page limit. There are so many people on this paper, and they're all from different places. So underneath the people, it says affiliations are included on page 11. Took up too much space on page 1.
Another CZI.
Yeah. So this Talon guy did his PhD. I was looking him up. It looks like he did his PhD with the last 3 authors, including Rudolf, and that he's now at the Chan Zuckerberg Institute.
Okay.
I think we have to start with our own background to try to explain what this paper is. So this paper is a 3D version of a 2D technique that both Linnea and I, really Linnea.
Well, so yeah. Okay, go ahead, and then I'll interrupt.
Okay.
Sorry.
So there is a kind of microscopy that we have done before that allows us to gain information about the molecular structure that could not be viewed via normal microscopy. And so, for instance, if you have many tiny, nanometer or 10 nanometer thick rods all aligned together, they essentially create like an optical grating that affects the way that light goes through them. Not all aligned together and they're disorganized, then they just block light. But you can have, essentially little bits of biology interact with light in a way that polarizes that light or changes the polarization in that light. You can get a lot of really cool information on the nanometer scale about the orientation and structure of biological proteins, and you can learn if things are liquid crystals. I'll explain liquid crystals real quick. A liquid is where your position is random, or not random, but there's no lattice to it. A crystal is where there's a lattice to your positions. A liquid crystal is where the position is got no lattice, but the orientation has some pattern. So one version of a liquid crystal might be if you have a bunch of rods that are like a water, but all the rods are pointed in one direction.
Yes. And these use in everyday life, like your watch, your old digital watch screen is probably a liquid crystal interface. Some e-readers are liquid crystals. So this is like, a material that you find in your everyday life. But yeah, so we did a lot of microscopy in grad school to try to understand the liquid crystal properties of biologically based materials using polarization microscopy. But no?
Sure, yeah.
Okay. But this paper is slightly different, right? This is doing fluorescence anisotropy measurements.
Yep.
So we're still using polarizers, but now rather than measuring the material itself, it's anisotropy, so how much it polarizes the light. We're looking at a fluorescent molecule and how much its emission is polarized.
Yeah, so I kind of think of this a little bit like how we used to do our old second harmonic generation imaging of microtubules that had Alexa 647 on some of their tubulin. And this all makes me quite nervous because, rather than trying to look at the orientation of many little bits of biology, we've attached glowing bits onto that biology and are just kind of hoping that the structure is locally rigid enough that, like, if an actin filament is pointed in one direction and we've attached a light bulb onto the actin filament, that light bulb is also attached in the same direction.
Yeah, it's an interesting, it gets around a limitation of these label-free methods where you can probe a particular structure. So you can probe actin in particular and not get mixed up with intermediate filaments or microtubules. And a rigidity or that actin can be very hard to image through label-free microscopy because it's not polarizing the light inherently, but it adds an additional limitation of length scales and bond strength between the fluorescent particle and...
Yeah, so it seems to me like the technique essentially only works if you can get your fluorophore to be somehow rigidly oriented. And they say at the end of the paper that they really feel the limitation to this technology is not the optics, that there's 100 ways to go about this to make it work, that the limitation is fluorophore design. I do think, maybe they're definitely the experts, so, but I also was wondering what kinds of problems can you solve with this technique, right? Okay, so here's a thing that I think you could do with this technique that might be fun. So one thing that I know is if you're doing just normal label-free polarization microscopy, mitochondria light up really strongly, that their membrane bilayer has a tremendous amount of orientation. So in some ways, their membrane bilayer is a kind of liquid crystal, and that has significant optic properties. Another thing that I know is that I desperately would like to be able to measure the rate of ATP phosphorylation by ATP synthase 5, this rotor, on the membrane.
Okay.
I know that some people tried to attach a fret pair onto the rotor, and we're going to think that every time that it went around, it was going to activate that fret pair, but that it was too noisy because there was too many rotors. Well, here's a different very silly thing you could do. You just put one fluorophore on the rotor, and you take images at different time scales. At some, time scale, you're going to go through an entire rotation of the fluorophore, and all of the orientation information is going to cancel out. And that ATP synthase is going to be the one thing in the mitochondria that has no signal whatsoever, right? Because it all canceled itself out. So then you move around your time scale, and you find at what point are you in sync with the rotational rate of the mitochondria.
Okay.
Would it ever work? Absolutely not. Of course not.
Yeah,
But
there's a lot of assumptions there.
But I think
that kind of experiment.
I think that there are a lot of fun things that you can do here.
I think a lot of membrane, I agree that you can do a lot of membrane studies with this kind of technique.
So here's my concern about what you can't do, which is the obvious place to use this is to go on a 3D pneumatic liquid crystal like Swan and Guillaume Duclos were making, and do some beautiful imaging of that has deep information about, the pneumatic order in the 3D.
Yeah.
And you'll get the same thing that you got when you did the first time, which is these 3D pictures that nobody can comprehend. They're not beautiful. They're so dense with information that nobody knows what to do with them. And that a tremendous amount of what you can do with this technology is create images that nobody can interpret. And that's kind of what happens in this paper.
And they allude to this, right? Where they're like, the most insightful way to look at this data is look at everything all at once. But that is impossible for anybody to do. So we've made this. A direct quote was, "Well, the peak cylinder visualization is the easiest to interpret reconstruction. The ODF reconstruction can reveal the subtlest changes that our system can measure. And the peak cylinder visualization is totally incomprehensible." So the easiest to interpret reconstruction, also just a 3D cloud of rods. Well, and it does get at that this really could be three-dimensional, confocal resolution data, but everything that they show is surface.
Oh, is that true? Everything that they show is surface?
It feels that way. They're in the middle of the GUV. They're so low density, we don't really get much signal. We're super uncertain. And then they have these...
oh, yeah. And then the cells are quite thin, too.
Yeah.
I didn't even catch on that.
And so, one of the major breakthroughs here is that you can now do these measurements in 3 dimensions. But yeah, again, you get hung up on these visualization problems.
Yeah, I did not catch that most of what they did was pretty 2D. I spent a lot of time thinking about their... So I know that this was a project almost 10 years in the making, that a lot of people got stuck on how to do this for a very long time. And the big sticking point was this reconstruction of you go get the data, and you've gotten the data in a very confusing manner where they have, kind of essentially 2 microscopes glued to each other at 90-degree angles.
Yeah, and you have to excite from both directions.
You excite from one microscope to the other microscope, from the other microscope to the one. Gary has a dye spim setup like this. I'm kind of disappointed that they did a dye spim setup just because it's such a tiny volume that you get to look at. And if you're going to go big, please go big. But they've done a tiny volume version that seems, it's good. It's whatever. But then they have Polarized. Essentially, they have, pole scopes on both sides.
Yeah.
And they're rotating that. And they talk about essentially the matrix that they have, that all the measurements that they take are in this G sub PV, where V is the view index and P is the polarization index. And you think about the size of that matrix, right? And then that you're going to try to reconstruct one of these spherical harmonics for every single voxel.
Yeah.
Right? And it's a massive
problem, and one that I don't think I totally understood their solution to, even after reading fairly carefully. So the point where I got stuck was this spatial angular point response. Do you understand what that is? Is that this thing that they show in 1E?
Yeah, so the way that I let me look at 1E real quick before I answer. No, I don't think that this has to do with 1E.
Okay.
The way that I view this, right, is you have two things. You imagine that for every point in space, there exists a little sphere that represents you're going to shine light on a fluorophore, and the fluorophore is going to shine light back. And how bright the fluorophore is going to be is going to depend on the angle that you shone light on it, right? And so you represent that with a sphere, and maybe the sphere has one big bright lobe, which is the direction that the flashlight is pointing, and everything else is dim.
Yeah,
right?
So those are these spherical blobby functions that they're showing all the time. Is that right?
Yeah, they call them ODFs, orientation distribution functions. Yeah. And, they're built out of some set of spherical harmonics, right?
I got that.
So each point in space gets an ODF, and so you get a little cube of 1,000 by 1,000 by 1,000
little
ODFs,
and that's what they plot in 2C4.
Right.
Yeah.
So that is the underlying what exists. You don't measure that, though. What you measure is a series of essentially intensity images, which is just brightness, in a cube. So you get a brightness cube, and you get one brightness cube for every polarization click that you do on the polarizers.
Yeah.
And you get another brightness cube for each of the microscopes that you've got. And then it turns out that because they kind of are going to tilt the laser beam a little bit to address a blind spot, you're going to get even more brightness cubes. So on the left-hand side of the equation, right, those are the brightness cubes that you
I got
measured.
that GPV is the brightness cube.
On the right-hand side of the equation, that's the truth. That's the many spheres.
But this is where I got confused.
The spatial angular point response function is this function that they've built, which is defined as the function that converts from one to the other.
Okay.
And so what they have to do is they have to solve what that function is.
Okay.
Right? And so the rest of this is, they go into Fourier space and they come up with a way to solve for one given the other discretely, because they can't solve it continuously for reasons I actually don't understand. It doesn't look... I don't understand what they mean by it's extremely computationally expensive to invert the equation. To me, it's either possible or it's not. And so I don't quite understand. But I'm sure that there are lots of subtleties there.
Yeah. I mean, they don't have the... I think the discretion makes sense because they're only measuring 6 different polarizations. So you might as well go discrete because you would have to interpolate the whole...
Yeah. And so it is pretty heavy, right? Where I got lost, right? I chunked through it, I think, a little bit more because I got really obsessed. Anyways, I'll talk about it. But where I got lost was where they actually go through the core algorithm and they go through this 4-step thing of they create the 3D spatial Fourier transforms, then they collect the Fourier coefficients from each polarization view into a 6x1 vector, and then they multiply each vector by a pre-computed spatial frequency, specific 15x6 matrix. This algorithm to get the solution... I'm sure if I stared at it for 2 or 3 days, I could recreate it.
But it's one of these things that even with Polscope, which I used all the time in my PhD, every time I had to go back and relearn how you compute from the 4 images, the birefringence and orientation.
And then I'm just going to read the sentence that they have right after this, because I love these sentences. It's a very well written.
Yeah, it's beautiful.
We found that directly visualizing the complete reconstruction, a 3D spatial distribution of ODFs, provided the most information about the sample, but was visually overwhelming for most applications. I just feel like they wrote it like humans. It actually kind of looks like in the discussion that screwed them over a little bit, because it sounds like some reviewers gave them a hard enough time that they dropped the temporal data, which I'm quite upset about. Reviewers, come on, don't make people drop data.
Yeah, I don't know. I didn't know if that was them being, you think that was reviewer instigated?
I don't think you would possibly put that in the discussion, that you had to drop some data from the paper. if it wasn't reviewer instigated.
But you don't think that the reviewers were like, why don't you just try doing some live cell stuff? It seems like it would work. And they're like,
that's another interpretation.
Yeah.
That's another interpretation. Okay, maybe. Okay, so then the coolest thing happens, which apparently happened in a previous paper, which is they find out that some of their rotations that they're trying to do are degenerate.
Yeah.
Right? So I always talk about this gimbal.
They're not degenerate. They're blind spots. They can't be measured.
I think that these two statements are equivalent.
Okay, I see. Kind of. I mean, like, it's that it could be one of these 4 blind spots.
Right. So I think that this is equivalent. Maybe I'm totally off, right? When you're trying to do 3-dimensional rotations, you might give yourself a rotation along one axis, a rotation along the second axis, and a rotation along the third axis. And it will turn out that there are rotations that are possible. They will cause 2 axes to kind of fall on top of each other so that you're no longer able to separate them. Right. And I always get obsessed with this idea as gimbal locking, because this is the old like Apollo rocket story of they only were able to have on board 3 gimbals rather than a 4th gimbal to prevent this problem. And so they just had a guy continuously hit one of the gimbals so that it wouldn't gimbal lock. And there's this like recording where one of the Apollo missions is taking place during Christmas, and they say, "What do you want for Christmas?" And the guy whose job it is to just knock the gimbals says a 4th gimbal. And that's always like really stuck in my head.
I can't believe you remember these things.
As a story. Well, I think the guy doesn't get to go to the moon. Like, he doesn't get to land because his job is to knock the gimbal.
Yeah. Okay.
And so I think that's essentially what's going on here, is that you have a certain amount of degrees of rotational freedom that you've gotten from the 2 microscopes and from the different polarizations that you can use. And it's not enough to prevent, essentially gimbal locking, and you miss out on some of the spherical harmonics that you really needed to measure.
And I loved the way they told this story. That they were like, we really thought that all we had to do was like take more,
God, it's so good.
More angles and over determine the problem, and it didn't work, and it didn't work, and why didn't it work? And oh yeah, this is the problem. I thought that was, rarely do you read a paper like that.
Yeah, I will say this paper is unbelievably thick, and it's got a lot of math. I really think that this is a great paper for like an optics course. Like this is if you got this, then you've got optics. I do think that this is high up there on some of the best papers I've read for just like how it's written.
Yeah,
like,
just the storytelling.
This is the last major paper that Rudolph gets to be on. I think that's a pretty good way to go out, right? Like that's a good end to the career. And I kind of think that's, a little bit of what this is, that this is a little bit of a swan song paper.
Well, he's not last author on this paper. He's not last author.
I don't know if this is a swan song paper for Rudolph. I wonder if this is a swan song paper for this technique. This technique has failed to gain traction for the past 15 years. It's only gained traction among some physicists. They put it in 3D. It's a hot mess in 3D. Other people are doing the same thing with super resolution, where it's much easier to figure out what the heck is going on because you have very few dots, and you can tell what's going on with 20 dots. They say that the biggest problem for getting this to work is the development of cool new fluorophores, where this will work really, really well. But to me, the biggest problem with this getting to work is that nobody's going to adopt it.
Is it an adoption problem?
It's hard to figure out where to use it. It's hard to figure out how to use it. It's hard to build this device. I mean, we have built light sheets. We have built polescopes. We are maybe one of 50 people on the planet that's true for. And if you told me that we had to spend a year building this, I would say, I don't know if I can get it done in 1 year.
I feel that we could build it. But again, what's the question that it's going to answer? And how is it going to answer it? Like, is it worth it? Is really the question. Like, one of the things that we struggled with Polscope was that it is only measuring in this 2D plane, right? So if you have a rod pointing in the 3rd dimension, you have no information about that. And it can actually distort your signal in the plane that you are measuring. So this would get around that. But how, like, that is in the system I was studying is so clearly a 2nd or 3rd order effect. Yeah, what kind of question would I really be using?
Well, you want to know if Chlamydomonas and Volvox and many other pyrenoid algal species, if those pyrenoids are liquid-like or liquid crystal-like.
Yeah.
And that if it's sometimes true in some that they're liquid crystal-like. And this would be a way to mass measure that and faithfully measure that.
But you have to incorporate a fluorophore.
But you have to incorporate a fluorophore, yes.
In a live cell. So at that point, why not just do FRAP?
You can do autofluorescence.
Yeah, so you have to find something in the pyrenoid that autofluoresces.
And also nothing else is allowed to autofluorescence
And
that
that
wavelength.
autofluorescence has to be polarized.
Yeah.
So
Does
that's,
the autofluorescence have to be polarized?
I mean, the emission has to be polarized, right?
I'm trying to think about that statement. I mean, what they kind of say is that if the light is coming in a direction, it tends to come out perpendicular to the plane that it's pointed in.
But they talk about at the end, let's see, where do they say it? Well, we have assumed that excitation and emission dipole moments are parallel. Some fluorophores have greater than 20-degree angles between these moments, characterizing the complete orientation distribution of an ensemble of molecules with misaligned dipole moments would require an extended version of the ODF beyond the spherical distributions discussed here to distributions over SO3. SO. I don't know what SO is standing for here.
This is like a rotational group.
Okay. But anyways, so if your excitation and emission dipoles aren't parallel, then that's a property of the fluorescent molecule itself. So if your autofluorescence isn't in this way, if it has a greater than 20-degree angle, which how do you know that about autofluorescence?
I think the concept is most things have excitation and emission dipole moments that are parallel, right? If you have an electric dipole moment, right, it's roughly the same going in as going out for most molecules that exist, right?
Okay, but most molecules are not autofluorescent. So I don't think that this assumption would hold in an autofluorescent. Like, I would want to test that if I was trying to make fluorescence anisotropy measurements of an autofluorescent structure.
I think that the statement that excitation and emission dipole moments are parallel is an important statement for when second harmonic generation works through autofluorescence. So I think that this is used in label-free biology.
Okay. I don't know enough, but I'm saying I wouldn't make that assumption of an autofluorescent protein because they have two citations here saying that there are fluorophores out there known to have greater than 20-degree difference.
Sure. But do you think that fluorophores are particularly engineered to have this parallel excitation and emission dipoles?
No, I think fluorophores were stumbled upon and are only recently being intelligently engineered in any way.
I would assume that molecules have the same distribution of this as fluorophores do.
Sure.
So that most molecules have parallel excitation and emission dipoles.
I just feel that is like, what is your, yeah.
Well, if they think that most fluorophores...
They don't say that. They don't say we think most fluorophores are aligned in this way. They say we have assumed this. That doesn't say that we think that this is a case that works, right?
Okay. You're just skeptical. That's
I'm not
fine.
skeptical. I'm just saying that I think that there's a big hurdle to using this in autofluorescence.
I don't think we will ever find out the answer because I don't think anyone will adopt this.
I mean, we could adopt it. You just suggested a project.
You just gave a whole big argument for why you're not going to adopt it.
Okay. I don't know. I would adopt it if there was the right question that I really thought I could answer, but that's the limitation for me. And also the length scale. I mean, I get this is a thing that I hadn't thought of before about polarization microscopy in general, which is just that you're probing a very particular length scale of local molecular order. And if you're seeing order, like here, they're like, oh, look, it can go over larger length scales. But yeah, your microscopy isn't telling you that. Your larger image is telling you that.
While scrolling to argue with you just now, I have stumbled upon another sentence that I love, in which they are, again, discussing that the images that they are showing are completely impossible to understand. And they say, the density reconstruction, movies 1 and 2, gives a view that is familiar to fluorescent microscopists, with brightness encoding the density. Here's a little bone. Look, this is an image that you recognize as an image. Just believe us that the rest of the images are also images.
What do you think is intellectually beautiful about this paper?
I think that the way that they have gone about figuring out this spherical distribution function, this orientation distribution function for each pixel in space, by saying there's some images that we get, there exists some orientation spatial distribution function, there exists some equation that transverses the two, we are going to solve for what that equation is a beautiful way of framing this question in a way that isn't impossible. And I think this is the last decade where we will see people go to frame questions in that beautiful way that I really expected when I opened this paper for them to say, and then we threw AI at it and it gave us an answer.
Yeah.
And I know they tried to throw AI at it because we talked to Gary that they had a whole AI symposium, not Gary, we talked to Rudolph that they had a whole AI symposium at the MBL just dedicated to doing this problem with AI. That's not the way that they went in the end. They went with something that could be part of a course that really gives me faith in a measurement where a lot of stuff is showing up and the results look very complicated. And so I find that really beautiful.
Yeah.
Is there something that I didn't understand? I mean, we talked already about where I got lost in the math, which is this core algorithm where they start talking about the matrix multiplication of the Fourier transforms. And then I solved for myself, but I'll just say I didn't understand why they weren't including L1 and L3 for the spherical harmonics. And I went and looked up what the spherical harmonics looked like. And L1 and L3 are pretty useless, funky. So that makes sense.
I had a question. They, in their first results section, they say, by detecting light with an objective that does not collect light from the entire half space, we preferentially detect emitters whose dipole moments are perpendicular to the optical axis of the detection objective.
Yeah, so my interpretation of that, I don't know where that is, but like one thing that I learned from Chehong a long time ago is, right, like you have all the light coming, let's say you have a plane, and you have a z direction up and a z direction down. So all the light that goes in the z direction up, that's one half space. All the light going in the z direction down is the other half space. Sometimes when you go in with a condenser and an oil condenser, you're really collecting most of the light from an entire half space. You're really trying to bend almost all of the light back into your optics. But a lot of the time you go in with a very narrow objective and you're actually rejecting the vast majority of the light that you could be getting. So I think that's what that sentence is about.
Okay, that makes sense. But then, yeah, it says that numerical aperture less than the index of refraction. And so then shouldn't it matter which, so they have two objectives with two different NAs.
Yeah, and so they actually make a rule in the mathematical reconstruction here where they are only going through certain equations up to some diffraction limit calculated by the numerical aperture. I find their choice of objectives for this very confusing. Yeah, I understand that these are classical pairings that you use these two objectives together. In fact, we almost bought these two exact objectives for our setup, and we ended up going with a slightly different setup. Yeah. But yeah, again, if I had done it, it would have been two objectives with the same NA, and they would have been long working distance.
But that's because your things are big.
That's because my things are big. That's because my interests are different. This is how they.
If you could have had one thing added to this paper, what would it be?
I'm really tempted to say live data, but they specifically said in their paper, no, we don't have that yet. We're sorry. And their thing about not having live data is that they're worried about the timescales of acquisition, which are very slow because it's this PolScope click thing that we know is very slow and doesn't really need to be. And they also, but I'm just like, go get a slower system. My chick lungs, don't move visibly over the course of an hour. I have to take movies for like 3 or 4 hours before I see any like visible motion of material.
Sure, but they're measuring on length scales that are diffusion, right?
Go get a bigger and slower system. So I think that's what I would have. Well, I guess no, the real answer is not only would I have liked a bigger and slower system, but I would have liked a genuinely three-dimensional system.
Yeah.
And that being said, though, I'm pretty happy with what I got here.
Yeah, I think it's a beautiful paper. I think that doing something like in outside of biology, I liked your idea of going back to Zvonimir type systems, or even before that, go to like just a smectic liquid crystal, right, and see what you get there, or something, maybe with less optical properties, but to really have a beautiful proof of concept and maybe uncover some
We're getting close to the end here, but I just want to. They say that they took inspiration for this solution from MRIs.
Oh, yeah.
Do you know what they were talking about?
No, they were like, it's like dye MRI or something.
Yeah, I started Googling it, and then I was like, oh no, this is going to be a long detour. I don't have time for this right now. So what do we think are the deepest takeaways from this paper? What did we technically learn?
Yeah, think hard about things. Like, that is the deepest takeaway, I think, is like, if you have data and it's not making sense, you've made a measurement and you know you need to disentangle it from, like, what you want is not what you measured. Think really hard about what it is you want and figure out how to get it from what you've measured. Would you do this for actin? Like, you do look at actin. Would you care about the alignment? And would you be able to get more out of... So one of the things I found frustrating in my PhD doing PolScope was that by the end of my PhD, nobody did PolScope. Everyone just used fluorescence measurements and computers to pull out the same information. And it wasn't quite as good, but it was good enough for the modeling.
Actually the same information though, right? People...
Sure, it's not actually the same information, but for connecting it to physical models, it was good enough. And so would you care enough about the molecular alignment of actin in your apical constriction to do this kind of thing? Or would you just look at the fluorescence image and say, well, it looks like it's kind of aligned, or it looks like it's kind of not aligned?
Yeah, I think I would just do the fluorescence image. I'm generally not interested in this kind of thing. They have this paragraph, it's the very last paragraph of the paper, that I deeply don't understand, where they say fluorescence and anisotropy can be used for homofret measurements of molecular binding. I don't know what that means. And an early non-tilting variant of the system described here was used to make such measurements. We hope that future efforts will encode additional physical parameters, such as force and voltage, into the orientation and rotational mobility of fluorescent probes, with readouts enabled by systems like the one described here. Well, if you say that I can use this system somehow to measure force or voltage, sure, I'm super excited about that. But where did this paragraph come from? Yeah.
I mean, they cite two papers, right? 60 and 61, which are, homofret fluorescence anisotropy imaging as a tool to study molecular self-assembly in live cells, and a genetically encoded biosensor strategy for quantifying non-muscle myosin 2 phosphorylation dynamics in living cells and organisms.
I've clicked on one and it already looks pretty exciting. And so, I think that's it. If you have feedback, let us know. We put up a journal pub on
the Patreon.
It's a free Patreon. It's just to make a little bit of like an access wall so that not everything we ever put out is just out there for Google to search. And we'll do that a couple more times, trying to iterate on the format until people like it. If you have paper suggestions, send them our way, because we have a lot of difficulty thinking about what papers might make okay conversations. I loved reading this paper. I don't know what people think about this episode.
I thought it was a great episode.
Oh, yeah. Okay, great.
New episodes of the Lemma Journal Club come out on Mondays. And
you said that so cleanly. That sounded like, professional voice.
Yes, we are professionals here. Okay.
All right, bye.
Bye.